Hello guys, welcome to my YouTube channel. So today we are going to start a new lecture series on bioreactor design and analysis. So first we will talk about batch cultivation with special reference to batch bioreactors. Okay, so now there are mainly four phases that are observed in batch cultivation. Number one is the lag phase. So what is lag phase? Like when you add cells to a culture media, what happens? This type of phase occurs immediately after inoculation and is a period of adaptation of the cells to the new environment. That means when you add new cells to a media, the cells take some time to adapt to the new environment. Okay, immediately after inoculation. So that time, that phase is called as a lag phase. So in this phase, what happens basically, cells reorganize their molecular constituents because they are transferred to a new environment. Not only this, the cells also synthesize new enzymes during this phase. And basically, this is a case of adaptation to the new environment where the cells basically adapt to the new environment by changing their internal machinery and by reorganizing their molecular constituents and synthesizing new enzymes so that they can cope up, they can adapt to the new environment. Now after this lag phase comes the exponential phase. Okay, so what happens during the exponential phase? This is also known as the logarithmic growth phase. So basically this is called as the exponential phase because the cells multiply exponentially during this phase. Okay, so during this phase, because the cells multiply exponentially, you will see there is a rapid increase in cell mass as well as cell number density, which increases exponentially with time, and this is also called as a period of balanced growth. Okay, why it is called balanced growth? Because in this phase all the components of a cell grow at the same rate. Okay, so that is why you will get a linear curve during this phase. So on the right hand side, if you observe closely, this is a typical growth curve. So from here to here, this is called as a lag phase, during which the cells adapt to the new environment. Okay, so after lag phase comes the exponential phase. So this straight portion that you will notice, this is the exponential phase. Now because this is a period of balanced growth in which all the constituents of cells grow at the same rate, so you will get a linear sort of curve during this exponential phase. Alright, and between the lag phase to the exponential phase, that is when the curve starts, entering the exponential phase from the lag phase. So this portion is called as the period of acceleration or the acceleration phase. Okay, so this is called as the acceleration phase. So after exponential phase comes the stationary phase. What happens? So stationary phase starts at the end of deceleration phase. So this is the exponential phase. As you can see on the right hand side of the figure, I have drawn the exponential phase. So after exponential phase, from here comes the stationary phase. Okay, so this is the stationary phase, and between the exponential phase to the stationary phase, that is when the curve starts entering the stationary phase from the exponential phase, this is called as the period of deceleration or the deceleration phase. So remember here two things. When the curve starts entering the exponential phase from the lag phase, it is called acceleration phase, and when the curve starts entering the stationary phase from the exponential phase, it is called as the deceleration phase. So it is said that stationary phase starts at the end of deceleration phase, that is after the exponential phase. And here the net growth is 0. Okay, net growth is 0, but that doesn't mean that the cell division, it means that the cell division is 0, but that doesn't mean that the cell number is 0. Okay, so there is no cell division, but there are certain number of cells present in the culture media. And when does it happen? When is the net growth 0? When the growth rate is equal to the death rate. So the number of cells that are forming is equal to the number of cells that are dying. Okay, so then only you will observe the net growth to be 0. So on the right hand side, if you notice, this part of the curve is almost parallel to x-axis. Okay, so here there is almost no change in the number of cells. Almost here with time, as you can see, it is it is really constant, nearly constant. So this is called as the stationary phase. Why? Because this is here, as you can see, the growth rate is constant, because number of cells that are forming is equal to the number of cells that are dying. And even though the net growth is 0, but this is very important, cells are still metabolically active and produce secondary metabolites. So the net growth is 0 during the stationary phase, but that doesn't mean that the cells are not metabolically active, or that doesn't mean that the cell number is 0. Cells are metabolically active and are synthesizing secondary metabolites. Secondary metabolites like those which are not required for growth, like antibiotics. Okay, so here only the thing that is happening is the number of growth rate is equal to the death rate, but the cells are still active and they are synthesizing secondary metabolites. So after death phase, after stationary phase comes the death phase, in which the dead cells lies and intercellular nutrients are released into the medium, and this basically happens because of release of some toxic end products from the cells, or because of nutrient depletion. So what happens when you grow the cells for a long period of time, the cells utilize the nutrients. Okay, and sometimes if the cells are the cells are in contact, close contact, or it can also happen that after growth, extensive growth, the cells may start to release some products or which may be harmful for other cells. Okay, so in that case the death of cells occur. Or it may so happen because your cells, we are growing cells for a long period of time, the nutrients are depleted, no more nutrients are there for rest of the cells to utilize, then also death phase can occur. So on the right hand side of the figure, as you can see, after the stationary phase, here comes the death phase. Okay, so there are mainly 4 phases of cell growth that you can observe. Now we will see a relation between division rate and specific growth rate. Specific growth rate, if you observe my previous 2 lectures on chemostat, you will know that the specific growth rate is denoted by mu. Okay, and the division rate is denoted by delta. Here we will come to it. So delta is defined as a division rate of the cell. So first, let us see how we can relate this division rate and the specific growth rate. Suppose we take C0 to be the initial number of cells, and suppose that C0 cells takes time t to divide n number of times. Okay, so after time t, the final cell concentration is given as Cn is equal to C0 into 2 to the power of n. Why? Because from 1 cell 2 cells will form, 2 cells 4 cell, 4 cell to 8 cell, like it will increase in geometric progression. So after time t, the final number of cells will be initial number of cells multiplied by 2 to the power of n, where n is the number of times or number of generations a cell has divided. Now the division rate is defined as dn dt, that is the change in the number of times the cell is divided, rate of change of number of times the cell is divided. So this is called as the division rate. So if we take the logarithm of this equation, okay, so this is denoted as Cn is equal to C0 into 2 to the power n. If we take logarithm of this equation, we get ln Cn is equal to ln C0 plus n log n ln 2. Okay, so if we take the logarithmic of this equation, we get ln Cn is equal to ln C0 plus n ln 2. So what will be the value of n then? N is equal to ln Cn minus ln C0 by ln 2. Okay, so this is basically what we get from here. Now what we have defined, you remember this, that the division rate is actually the rate of change of the number of times the cell is divided. Okay, so this is the final expression for n. Now if we differentiate this expression with respect to time, what will happen? This part ln C0 will be constant. Okay, so this part ln C0 will be constant, and for that we will get 0. So only for which part will we divide? We will consider this part ln Cn by ln 2, this part, because ln C0 by ln 2, this part is constant. Okay, so if we differentiate this expression, we will get the value of delta, because we are interested in finding the value of delta. So delta is actually d of ln by dt whole divided by ln2. Now how did it came? If I write it here, so by applying distributive law, it will be ln by ln2, okay, minus of ln naught by ln2. So if we differentiate this, what will happen? D and dt will be written as d of ln by dt whole divided by ln2, and because the right hand side is constant, this part is constant, so it will be 0. Okay, so this part is a constant. C naught is constant because initial number of cells is constant, and ln2 is again constant, so this part will be 0. So now this is actually what? This is actually the delta. So you get this expression, delta is equal to d of ln by dt whole divided by ln2. Now we have Monod equation. So if you observe Monod equation, you know then that Monod equation can be written as 1 by Cn. Okay, so this you can write it in Monod equation by dc and dt. Okay, sometimes people also write Monod equation as mu is equal to, mu is a specific growth rate, 1 by x dx dt, same thing. Okay, some denote it as Cn, some denote it as x. X is the biomass, okay, of the cells. So both are same things. So if we write it here in this form, then dc and dt, so we will get it as d of ln by dt. Okay, so now, so from here, by relating these two expressions, we will get delta is equal to mu by ln2. Okay, so delta is equal to mu by ln2. So this is the relationship between the division rate delta and the specific growth rate. Now growth rate, general growth rate is denoted as Rn, and Rn is defined as dCn by dt. Okay, so this is a general expression of growth rate, simply growth rate. Sometimes people also write growth rate as dx dt, same thing. People denote cell biomass as x, some people denote as Cn, same thing. Okay, so now what you can relate it here is, we know, we have already seen that in the exponential phase what happens, mu is mu max. Why mu is mu max? Actually the specific growth rate is defined as mu max minus kd, or the net specific growth rate is defined as mu max minus kd. Okay, mu max is the specific growth rate under exponential phase, and kd is the constant, rate constant in the death phase. Because we consider in exponential phase, we consider only growth, we do not consider any death of the cells. Okay, so kd is taken to be as 0. So mu or mu max, mu net is taken to be as mu max, and this is only applicable in case of exponential phase, mind it. Okay, so this is only applicable in case of exponential phase, not in any other phase. So what is happening, because mu is equal to mu max at exponential phase, which is a constant, because as you can, if you remember the graph that I have shown, the cell concentration graph here, this is the lag phase, then for exponential phase it is increasing linearly, and then you have the stationary phase. So for this portion of the graph, this is linearly increasing. So in this case the specific growth rate is constant, which is equal to the maximum specific growth rate. Okay, So here specific growth rate is constant, which is equal to the maximum specific growth rate because it is constant during the exponential phase. From this relationship, mu is constant, ln2 is constant, so delta is also constant. So during exponential phase, what happens? Delta or the division rate is also constant, but growth rate is not, because the curve is still increasing in the exponential phase, right? That means the growth is happening. So the rate of growth is not constant, but the specific growth rate is constant and the division rate is also constant. That means the bacteria or whatever cell you are taking, that is dividing at a fixed rate during the exponential phase. Now we come to design equation for batch reactors. So first, the most important thing to start for design equations is the mass balance. For mass balance, we know the general expression or the equation of mass balance is accumulation of mass, denoted as dm/dt, is taken as input minus output plus generation minus consumption. So in batch, what happens? We give all the substrates and cells at a time, and then we close the system, and then we run the reactors, and after some time we take out the products. So in batch reactors, we basically do not consider the consumption. Okay, so consumption is taken to be as 0 in batch reactors. So the expression becomes accumulation is input minus output plus generation. Now dm/dt. Okay, so this should be the mass balance. That means we should have an expression of mass. Okay, so it is written as dm/dt is written as v dx/dt. Why v dx/dt? Let me come to the point. dx/dt is actually a rate. Okay, so that I have already told you, rate of cell growth. Okay, so its unit is moles per liter per second. Okay, if you multiply it with liter, okay, then you get moles per second. This is when you do mole balance. Okay, and when the unit of rate is in moles per liter second. Suppose the unit of rate is in kg per liter second. Okay, so then you multiply it by volume to get kg per second, and kg per second is what? Rate of change of mass with time. So when you do mass balance or mole balance, you multiply the rate with the volume. Okay, so you multiply v dx/dt, accumulation, this is the accumulation. Okay, so this is v dx/dt, this is the accumulation of mass. Input is 0 because you do not what happens in batch bioreactors, you put all the substrates and media and cell everything before the start of the batch reactor. Okay, you do not put anything after the batch reactor starts. Okay, so therefore we consider input to be 0. So nothing is input once the reactor starts. Okay, so input is 0, output is 0, and the generation is vrx. Okay, similar logic, rate of generation of biomass is rx, you multiply it by volume to get the mass balance or mole balance. So this is the generation expression, v into rx. Okay, this is the input is 0 and output is also 0. Okay, so what happens, what you are getting, v dx/dt it's basically v into rx. Okay, so v dx/dt is basically v into rx. So this v and v can cancel, so rx is actually what? Rx is actually dx/dt. So this actually proves again that the rate of biomass generation denoted as rx is actually rate of change of biomass with respect to time. All right. Now dx/dt is equal to mu x and dx. So this dx/dt is defined as rate of biomass generation with respect to time, and it is defined as, now dx/dt is taken to be proportional to x. Okay, this taken to be proportional to x. So suppose we define a constant mu which is called as the specific growth rate. So dx dt will be equal to mu x. Alright, and what is mu by Monod equation? Mu is mu max into x by km plus s. So this is the final expression, dx dt is equal to mu max into s by km plus s. Okay, now we have seen that dx dt equal to mu x. Now if we substitute in this equation, mu is equal to mu max into x by km plus s, that is the Monod equation, and x is equal to x naught plus yxs s naught minus x. So x is the final biomass concentration, x naught is the initial biomass concentration, y is the yield coefficient, s naught is the initial substrate concentration, s is the final substrate concentration. From where does this expression comes? This expression comes from the definition of yield coefficient. If you look at my previous lectures on chemostat, you will see that I have defined that yxs is defined as change in biomass by change in substrate. Okay, so this is taken as s naught minus s. So by transposition you can easily get this. So if you substitute it, you get this and integrate. Okay, so you will get this long expression. So this is the final design equation for batch reactor. This is the design equation. This is very important. Now let us see specific, because one of the most important phases of batch reactor is the exponential phase, because whatever calculations we do, we consider the exponential phase only. Okay, remember this. We do not consider other phases, lag phase, stationary phase, death phase, because it will make our problem or make our analysis more complicating. That's why we do everything. Every calculation is done on exponential phase where the KD value is taken to be 0. So let us see the growth kinetics. So dx dt is equal to mu net into x. So rate of change of biomass is equal to net specific growth rate multiplied by the biomass concentration. If we integrate this with respect to time, we get ln x by x naught is equal to mu net into x. So we are integrating this expression. Okay, so what are the limits we are putting? At x naught, that is the initial substrate concentration, is initial biomass concentration at t is equal to 0. Okay, and the final biomass concentration, which is x, at t is equal to t. So if we integrate this between these limits, we get ln x by x naught is equal to mu net into t, or x is equal to x naught e to the power of mu max into t. Okay, now for doubling time, and this is very important. So for doubling time, what does doubling time is? Doubling time is the time taken by the cells to double itself. So suppose we have this expression, we can start from this expression itself. So it means doubling time is the time taken by the cells to double itself, that is the final biomass concentration will become twice the initial biomass concentration. So x is equal to x naught, 2x naught. Okay, so here it will happen, if we substitute this value 2x naught by x naught, it will be mu net into, so suppose we designate this t as tau d. So tau d value will be equal to this x naught will cancel, so tau d values will be equal to ln2 by mu net. So this is what I have written, and ln2 value is 0.693, so it will be 0.693 by mu net, and it is actually inverse of 1 by delta, because if you remember, delta is mu net by ln2. I've taught you. So this mu net by ln2, here you are writing ln2 by mu net, that means that it is the inverse of 1 by delta. So this is the relationship between the doubling time and the net specific growth rate, as well as this is the relationship between doubling time and the division rate. In our subsequent lectures, we will see more design equations and more fundamental aspects of batch bioreactors.